Hello everyone and welcome to our channel Mootechie. It's wonderful to have you here as we dive into a fascinating topic in chemistry, the colligative properties of solutions. Let's get started. Now let's begin by understanding a key idea. Solutions have different properties than either the solutes or the solvent used to make them. These properties can be divided into two main types, colligative properties and non-colligative properties. Non-colligative properties depend on the identity of the dissolved species and the solvent. Moving forward, we'll focus specifically on colligative properties. So what are they? Colligative properties depend only on the number of dissolved particles, that's molecules or ions, small or large in the solution, and not on their identity. There are four main ones we will explore. 1. Osmotic pressure. 2. Vapor pressure lowering. 3. Boiling point elevation. And 4. Freezing point depression. 1. Osmotic pressure. Let's explore the first one, osmotic pressure. To understand it, let's first talk about diffusion in liquids. Substances tend to move or diffuse from regions of higher concentration to regions of lower concentration until the differences in concentration disappear. For example, by placing water, the solvent, on a concentrated aqueous salt solution, the salt moves into the water layer and water moves into the salt solution until the new solution becomes uniform. This image illustrates diffusion, showing movement from an area of high concentration to an area of low concentration. Now let's take this a step further with osmosis. Imagine we separate a concentrated solution from pure water using a semi-permeable membrane. This membrane allows the passage of solvent, but prevents the solute. In this case, water will diffuse from the solution of low solute concentration to the solution of higher solute concentration. This special diffusion of solvent through a semi-permeable membrane is what we call osmosis. The next diagram shows this setup. On one side of the semi-permeable membrane we have a solution and on the other pure solvent. The solvent moves into the tube and the height of the solution will rise until the hydrostatic pressure exerted by the column of solution equals the osmotic pressure. So what exactly is osmotic pressure? It's the external pressure that must be applied to the solution in order to prevent it from being diluted by the entry of solvent via osmosis. It's like pushing back against the natural flow of water to maintain balance. Van 't Hoff equation for non-electrolytes. Coming up, we'll discuss the osmotic pressure of non-electrolytes, which are substances that do not ionize. For these, osmotic pressure is proportional to concentration. Twice the concentration means twice the osmotic pressure. It's also proportional to the number of molecules. So the osmotic pressure of two solutions having the same molar concentration are identical. This leads us to the Van 't Hoff equation. Van 't Hoff stated that there is a proportionality between osmotic pressure and concentration and absolute temperature. This is generally for diluted solutions. He suggested a relationship analogous to the equation for an ideal gas. He proposed that the osmotic pressure in a diluted solution was equal to the pressure the solute would exert if it were a gas occupying the same volume. The equations show that osmotic pressure, pi, is equal to molarity, m, times the gas constant, r, times temperature, T. It is also equal to molality, m, times the gas constant, r, times temperature, T. Here, the gas constant is represented by r. The form using molarity is known as the Van 't Hoff equation, and the form using molality is the Morse equation. Osmotic pressure for electrolytes. Now what about electrolytes? They dissociate into ions, which increases the number of particles formed and therefore increases the osmotic pressure. For example, sodium chloride ionizes into two ions, so its osmotic pressure will be twice that of a non-ionized substance at the same molar concentration. For potassium sulfate, it's 3 times, and for iron chloride, FeCl_3, it's 4 times the effect. The general equation becomes, where pi is osmotic pressure, V is volume, I is the dissociation factor, Van 't Hoff factor, N is the number of moles, R is the gas constant, and T is temperature. For a strong electrolyte, I is the number of ions produced by ionization. For a weak electrolyte is the total number of particles, ions or molecules, divided by the initial number before ionization. For a non-electrolyte, AI is simply 1. 2. Vapor pressure lowering. Next, let's explore vapor pressure lowering. When a non-volatile solute is dissolved in a solvent, the vapor pressure of the solvent is lowered. This happens because solvent molecules on the surface that can escape into vapor are replaced by solute molecules that have little, if any, vapor pressure. Why is this a colligative property? It only depends on the number of dissolved solute particles, not what they are. For an ideal solution of non-electrolytes, the vapor pressure follows Raoult's law. The vapor pressure of a solution, Pa, equals the mole fraction of the solvent, XA multiplied by the vapor pressure of the pure solvent, P to the power of 0 underscore A, colon. We can also express the relative lowering of vapor pressure as, which equals the mole fraction of the solute, XB, colon. So the absolute lowering of vapor pressure delta P is given by, this shows that the lowering of vapor pressure is proportional to the mole fraction of the solute. 3. Boiling point elevation. Now let's move on to boiling point elevation. The boiling point of a liquid is the temperature at which its vapor pressure equals the atmospheric pressure, which is 760 millimeters of mercury. For a solution, the vapor pressure of the solvent is lower at any given temperature. Therefore, a higher temperature is required to boil the solution than the pure solvent. The graph shows two curves, one for the vapor pressure of the pure solvent and one for the vapor pressure of the solution. The pure solvent boils at a lower temperature and the solution boils at a higher temperature, with the difference labeled as delta T underscore B. We can calculate this change in boiling point, delta T underscore B, using the formula. Here M is molality, K underscore B is the boiling point elevation constant specific to the solvent. For water, it's 0.51 degrees Celsius per meter, and I is the Van Hoff factor, representing the number of dissociated moles of particles per mole of solute. 4. Freezing point depression. Finally, let's understand freezing point depression. The normal freezing or melting point is the temperature at which the solid and liquid phases are in equilibrium under 1 atmosphere of pressure. Adding a solute decreases the vapor pressure and therefore decreases the freezing point. Think of it this way: for a liquid to freeze, it must achieve a very ordered state to form a crystal. If there are impurities, like solutes, the liquid is less ordered. This makes a solution more difficult to freeze than the pure solvent, so a lower temperature is required. The figure illustrates this, showing the freezing point of the solution is lower than that of the pure solvent, with the depression labeled as delta T underscore F. In analogy to boiling point elevation, we calculate the freezing point depression using the formula. The negative sign indicates the freezing point of the solution is lower than that of the pure solvent. Here, M is molality, K underscore F is the molal freezing point depression constant. For water, it's 1.86 degrees Celsius per meter, and I is the Van Hoff factor. It's important to note that both freezing point depression and boiling point elevation are a direct result of the lowering of vapor pressure. Thank you. See you in the next class.